Hello, am I audible? Hello, am I audible? Hello, and is my screen visible? You can type if you don't want to talk and let me know. I just need a feedback so that I understand that everything is visible and audible.
Fine, fine.
Okay, thank you. Okay. Yeah, so did you go through the third week's lecture? Did you find difficulty in understanding something? First, we'll talk about what is there in the third week's lecture, then we'll talk about solve some problems so that it helps you to solve assignment problems and then exams as well. So, yeah, I'll just take you through the lecture materials again, once again. So, then we'll discuss in between whatever we want to discuss. So, So yeah, to start with, so this week's lecture is on scheduling that you have seen. So scheduling, why is it needed to learn the foundations of physical systems? Basically, eventually we are talking about designing an overall system where there is a physical counterpart, digital counterpart to a physical machine. So the digital counterpart should be having a set of rules following which there will be a set of objectives, there will be a set of tasks to achieve a set of objectives that will be executed. So that set of rules comes from the scheduler. So the scheduler helps us understand when to execute which task and like that. So yeah, this is a brief overview of a system where CU denotes the control units. So in control units there are multiple tasks and they have, some of them have dependencies on each other, others have no dependencies maybe. So there are different way to handle these dependencies and decide when should we execute which one. That is done by a scheduler. So scheduler is also a task, but that is a high priority task, and that is usually like if you think in our OS, if you think about the scheduler that is scheduling all the tasks in our OS. By the way, how is it different than this laptop or this OS where the scheduler is also running and scheduling different tasks? How is it different in physical systems? Any idea? What do you think? So the thing is, basically here everything is happening in real time. But in OS, whatever you are doing, maybe I am trying to open a Chrome tab. That Chrome tab, if it doesn't open within, maybe if your system does not have that much memory to handle, then it will be opening after maybe 1 minute, and that won't bother you much. But in case of physical systems, these are usually real time systems, so you have to respond in real time. That is, there will be a certain deadline before which you have to definitely respond, otherwise some catastrophic failure might happen for the physical system that is being controlled by this particular controller or the digital unit. So that is where it is different, a bit different. But yeah, the scheduler, what I was telling, that is basically part of the OS itself. OS is also basically a software that is running in your processor. So you can consider that OS is also a processor, I mean a process or a task that is running in your processor. But that is something running there as a daemon process. Daemon process is like that initiates the this digital unit that I am talking about. So and it is in the, it has the responsibility to distribute resources among all other tasks that will arrive eventually on the way. So it will be there whenever I turn on the digital the module, the control unit in this case, and obviously they will be computing certain control inputs, and that will be communicated via certain communication bus, and from that communication bus others will get the data, or the plant will also receive the data, or the control units will receive the data and actuate to the plant. So obviously yeah, it goes on like that, you know the how it works by now. So yes, so there are obviously, you know, that the different types of processors and how different how they are designed, how their instruction sets are designed. Instruction sets meaning how we are basically communicating with the low level processing unit. So for that there are RISC CPUs, ARM, like ARM, PowerPC. These are also used in these embedded systems or the real-time systems, and there are different microcontrollers. An example can be Atmel, Atmega chip designed by Atmel. So there are different chips like that and different microcontrollers like that that are used in a system. There are other companies like Infineon that is heavily used in automotive sector. So yeah, usually what happens is there will be a host controller in a control unit. Maybe a host controller will be there, the communication controller will be there. Basically there are different kinds of tasks. Application tasks are there in host controller, communication tasks are there in the communication controller, and obviously the bus drivers will be there to communicate with the communication bus where I am going to eventually transmit my data or receive my data from. So like whenever we are connecting a certain system, maybe it can be a mouse or can be a keyboard to my laptop, basically we have to install driver so that whenever I am connecting that peripheral device, it understands, okay, I have to interpret the inputs that I am getting from this peripheral device. This is how I have to interpret them. So there should be a driver software that helps me understand that. So there are obviously communication bus drivers for that, and yeah, communication controllers are there for. There will be communication chips that understand that how maybe we are communicating using TDMA, maybe we are communicating using CAN. We read about CAN in our last lecture. So how CAN works, how should I prioritize a message, and how should I pack the data inside a CAN frame, maybe inside a CAN frame, the type of things. Please, you want to, you had something to say?
Sir, actually, I had some problem. Now I had rejoined it, so I missed something. This,
Okay,
so
fine.
that is why. Can you, because this is the toughest week, okay, and I could not solve any questions, sir.
May I know, which department are you from? I'm just curious because
Sir, I did MTech in 2009 in computer science.
computer science. Okay.
2009,
Okay. Now you are doing this
2009.
course as part of.
Now I'm working professional, okay, but
Okay. Okay.
still,
Okay.
so
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 are
I'm
you
I'm
learning
updating
this
it.
to teach your students? Is it?
Say again.
Are you learning this course to teach your students?
Yes, I was HOD also, but in electrical department.
Okay.
But now I am working, so I want to refresh my knowledge. So I have
Understood.
joined this.
Understood.
So
Yeah, it's good.
that's my
Yeah,
brief
it's good to
background.
meet you, Professor. So yeah, the thing is, basically, this course has a nice blend of two things. Since you are from electrical,
Sir.
you will have the notion of control theory, very basic
Yes,
level.
yes, yes,
Obviously, those are
yes,
there. Those will be eventually coming. Those will be easier for you. But this part,
yes.
there are two parts, as I told you. In for computer science part, there are the scheduling and real time, how real time data are access. All these things are there. And as part of theoretical computation, there are certain things like safety, reachability, timed automation, and all these things. So since you have a good background from computer science and electrical both, so eventually if you stay along, you will understand what is happening. Oh, I'll help you understand, don't worry. uh,
Thank you,
yeah,
sir. Thank you.
yeah. So basically what I was talking about. So there is a driver software that helps me understand how to pack a message. So there is a name for it. When I'm packing a message, I forgot the name. So there is a term that usually used in this domain. So when you are packing data inside a frame, and that frame is formed based on the um, communication module, like if you are using CAN, it will be packed in a CAN frame. If you are using something else, it will be packed in something, some other way it will be packed. So there are things like that. So that is why driver softwares are there, and basically communication controllers interact with the communication bus using these instructions from driver softwares, and they communicate whatever application is running in the host controller, the data from whatever application is running in the host controller. So this is the architecture basically in very crude way, obviously, because we don't want to go into the architecture part, because that is not our topic here. We will just understand how the overall system works. So the very necessary parts of it we will discuss about in this course. So yes, so the computation unit, or the CU or control unit, whatever you call it. So there are multiple tasks like sensing task is there, control task is there. So what does sensing task do? So we know from control theory, we know how do we receive a data from the plant. We have to know the plant current state of the plant in order to compute the control input. So once we sense that using our sensing task, from the obviously we will be invoking the driver software for that. We will follow the instruction from the driver software for that. So that will be this sensing task will be invoked by maybe the communication controller. So it will understand what is happening, what is coming through the bus, and it will receive the data and pass it to the control task that maybe is running in the host controller. And eventually after computation, there might be multiple tasks as well. It is a simplest architecture that is shown here. This is a simplest way to describe it. So there will be other tasks maybe in between. So after that, ultimately you are trying to compute certain things that is needed to be communicated with the plant or with some other control unit. Eventually that control unit will be actuating that particular control input to certain physical plant. So yes, there will be transmission tasks for that. So transmission task will be transmitting the message, and the message will be going via the bus, and again you are receiving it. Now if you notice, this is happening periodically. So yes, most of the tasks that are scheduled in such real-time OS, or they are usually periodic, and but they are application tasks. I mean, they are periodic since we are trying to guide the application task. So there are other tasks that accompany it, like sensing task or the transmission task or the reception tasks, all these things. So they are basically accompanying this particular control task so that it can run flawlessly in time. So yeah, so communication task, it is written about them. I'll skip these things. I'll go to the main thing. So yes, we'll talk about tasks when we are talking about the computation unit or control unit. We will refer them as tasks, and when we are talking about the data that the task is passing through the communication bus, we'll call them message. Okay, so if you notice, there are two things to schedule here. So in each control unit, we have to schedule the tasks in each communication bus. Obviously there can be multiple communication buses, because other than CAN there can be other protocols used, communication protocols used in the system. So for those protocols they may be following some other topologies as well, but if they are following a bus topology, then they will be connected to bus, and there will be different buses. Even for CAN there are different buses, I showed you in last lecture, right? So there are high priority buses or high speed CAN buses, there are low speed CAN buses. For different purpose there are different buses. Now there are different control units connected. Now there are two things to schedule. So basically in each control unit we have to schedule the tasks, in each communication bus we have to schedule the messages. So in this lecture we will learn how to schedule the, first we will learn about the processor task scheduling in the processor. Obviously we will learn it in a Uni-Processor setup, understand this very well. So we are considering the processor only has one core. So if there are multiple cores, it is handled in the same way. In each core, basically different tasks are assigned in the different core, or there can be other possibilities. Maybe one task is too heavy, like maybe you are running MATLAB in a real-time system. Maybe when you are running MATLAB or some big application like that in your system, basically they used multi-thread or multi-core as a resource, multiple cores as its resource. So it depends on how the code is written, how the controller code or the whatever code you are running, whatever task you are running, how its code is written. Depending on that, it will deploy different control cores, controller cores. So in this case, in this lecture going forward, we will be talking about Uni-Processor systems. Okay, so how to schedule tasks in a Uni-Processor systems, in a real-time Uni-Processor system. Okay, so yeah, so there are processing units. Yeah, the thing that I started with. So they are critical because there is a strict deadline, and they can be mapped to different processors. They might not need OS if it's self-sufficient. There are things like that. So I'll skip these things. So what is important, we'll stick to these bullet points. Basically, when I am trying to schedule, what do I have to decide? Which one to run before which one? So that is what I am trying to decide. So for that, first thing, there are multiple processors or there are multiple cores in a processor. Where to map which one, which task? That is the first thing. Ordering will basically help us understand which task to execute after which one. Timing, so when should I execute that particular task, even after I am ordering them differently, or what should be my constraints while I am doing it. So obviously whatever I do, there should be a constraint, otherwise I can do it whenever and whatever. It will look like a system that I am running a laptop or any other system. But in real-time systems, obviously there are real-time constraints, and along with that there are resource constraints. Okay, so yeah, both of the constraints in place. How should I schedule them? So there are different kinds of schedulers. In this case, we'll learn about different kinds of scheduling policies as well. So the scheduler may or may not support arrival of tasks. Usually in systems that are very complex and they use multiple control units, they have static mapping of tasks, like these tasks will be mapped to these particular control units, and the other tasks will be mapped to some other control units. So like that, it is fixed and no other task arrivals are supported. If some other task arrives, basically you know which all tasks will run, because the designer knows what are the things to run after how long interval. So those things are all pre-scheduled. Okay, so these things are decided beforehand. So there are different kinds of scheduler to handle these things. There can be a scheduling policy that helps you understand that whenever there is a new task arrival, how to handle that. There are policies for that, but we'll talk about them later. First, we'll start with something very static. So periodic and aperiodic and sporadic, these are the three terms that comes regarding real-time tasks, and that differentiate different timing strategies of the timing specifications, I should say, not strategies, timing specifications of different tasks. So the periodic tasks are basically, as you understand from the name, there is a fixed time interval after which its instances arrive. So notice this, when I am talking about when the task is arriving repeatedly after t time interval, I am calling it instances of that task or jobs of that task. Okay, so there can be multiple jobs of a certain task, and each job will be arriving once in every period for a periodic task. Now for aperiodic task, no such periodicity or the period exists. For sporadic task, again there is a lower bound for the periodicity, obviously, but it can come or it can be skipped at certain iterations. So it can be like that. It is irregular basically. Consider it's a there is a time constraint, there is a periodicity constraint, and but it is irregular. So sporadic task. So yeah, there can be precedence constraints on each task. What do I mean when I say precedence constraints? Basically, one task may depend on others, and based on that, based on the data from one task, like I told you earlier, maybe this, if you notice this, unless you sense a data that is coming via the communication bus, you cannot compute the control input. Okay, you can, definitely you can. Usually these are also implemented in an asynchronous way, but I'll come to that. I will not complicate things. Let's understand one by one. So the thing is, whenever you are receiving some data from the communication bus, you are able to make sense of that data. So that is what your sensing task is doing. Once the reception task receives the data, now unless you have that received data, state information of the plant, you cannot compute control input for the plant, right? So there is a dependency, as you see. The control task is dependent on the sensing task. So the sensing task must be executed before the control task. So there can be dependencies, and based on that there can be precedences. I mean, you have to choose one task should precede the other task. Anyways, so there are different constraints like this. I was talking about constraints, right? So when I say that the task is periodic, they are called their implicit deadlines. We'll come to that. Why I am bringing this up? Because I said there will be a deadline for each real-time task, but I am here, while I am talking about the timing properties, I am only talking about the periodicity. So in case of periodic tasks, the periodicities or the periods are considered as their implicit deadlines. That means that job that is coming in the current period should be done executing before the next instance of the current task comes. So, to understand even more, let's refer to a picture that is in the book, Lee Sheshia's book. This is taken from Lee Sheshia's book. So that is a very nice book, by the way. If you get a and if you can get a copy from somewhere, you can go through the real-time task scheduling section. That will help you understand what is happening here, and what we actually made this lecture based on that book only. So yeah, so here there are multiple timing properties, as you see. So release time is one of them. Release time is basically when the task is released. So ideally, when a task is released, it is ready to be executed. So there are different queues of tasks. An OS maintains different queues of tasks. What do I mean when I say different queues of tasks? Different queue means different queues defined. I mean, they are made for different purposes. One queue always remembers how many tasks are yet to be executed. If a task is transferred from that queue to a ready queue, basically that task is released. We consider that is the release time of the task. That is when the task is ready to be executed, but maybe it is not decided not to be executed by the processor, because the processor decides there is something more important to finish before I start executing it. And when it starts executing that particular task, that is basically the start time of the task, as you can see. So now there are different ways to handle this task executions. One way, as you can see, this is a very generic picture. Here you can see one way to handle it would be, if I see something more important is coming on the way, then I will stop execution of this particular task and I will preempt it with some other task. This is called preemption, preempting with some other higher priority or higher criticality task that is needed my attention right now. And when that is done execution, I will again restart from where I paused this particular task. So obviously the program has to be written accordingly, and based on that it will be starting from that particular checkpoint where you ended the task up till which you executed the task. Now if you see, it is finished execution at finish time, or Fi for the ith task. So this Ri release time, Si start time, and finish time Fi, these all three should be starting from Ri. I am basically here I am allowed to be executed. From there I am finished getting executed by Fi. So this duration is my response time. So this is the response time of the task, that is denoted with OI. Okay, and this is the execution time when I start and when I finish. If we add these two, obviously leaving the part where I did not execute at all, this is execution time. So execution time will be always less than or equal to the response time of a task, because response time includes starts counting from the time when the task is released and ready to be executed, but it might not be executed because there are some blockages, maybe some other tasks are using be getting executed, they are using the resource that I am supposed to use. So anyways, if you notice, if I compute if I count starting from when I started, the start time, and when I finished, if you see this duration should be before the deadline. So this deadline is basically a relative time interval that I am deciding. The designer decides that the task, that particular task Ti, must be executed before Di. Di mane when I am starting execution from Si, basically it should be done done with its execution at Si plus Di. So Di is a basically relative deadline, or we will call it deadline for now. So yeah, so there are these timing notions that we will be using going forward. So I just explained them so that it helps you understand. So yeah, so there are different ways to constrain with respect to time, constrain these task executions with respect to time. So one is hard real time task, there are hard deadlines or soft real time tasks, soft deadlines. What do I mean by hard and soft deadlines? Hard deadlines meaning you definitely have to meet the deadline. Basically your execution should be definitely done before or by the deadline. But soft real time tasks allows some deadline misses. If some of the instances miss some amount of I mean they are with a small margin, if it misses its deadline, we allow that in soft real time for soft real time tasks. So depending on the criticality of the task, we can decide which task should be hard deadline hard real time task and which tasks should be soft real time task. Obviously the critical ones must be following some certain hard deadlines, whereas some other non-critical tasks, maybe in a car you are pressing the media switch to turn on a radio or turn on the music, that can delay if there is something more important going on in the processor, but usually they are differentiated in different processors, so there will not be any overlap like that. But I am just giving an example what can be a task in such a safety critical system, that is where soft deadlines can be allowed, or yeah, it is like that. So non-preemptive and preemptive, as I told earlier, non-preemption meaning I will not stop executing the current task and let other higher priority tasks get executed. That is non-preemptive. And preemptive means basically I can pause the current task in case I am getting more important things to do at hand. If I have more important tasks to execute at hand, so I will stop execution of the current task, maybe I will finish execution of the other one, then I will start re-executing the current task. So that is preemptive way of scheduling tasks. And fixed and dynamic priority. Fixed and dynamic priority means when I am deciding which task to execute first. So I am deciding based on a fixed priority of the task. So fixed priority means basically I am always considering that task as the highest priority whenever it is in the ready queue along with the other tasks. I am always prioritizing that particular task. That is what a fixed priority means. And dynamic priority is basically the priority can change depending on the situation. Basically if I see there is a situation where another task needs execution right now, but that is not as high priority as the other task, but that needs to be executed right now, then I decide to execute it there and postpone the higher priority task. So these things are easy to say but not easy to write as an algorithm unless we have a structured methodology for it, right? So we'll learn how do we structure such a methodology of writing making scheduling policies. So priority can be different than deadline, or we can design the priority based on the deadline. It's designer's choice. The designer decides all these things, and how these things are done, those are again done by certain constraint solving certain constraints. There are certain constraint solving problems that are formulated, and then they are design there are these design parameters, like what should be its periodicity, what should be its priority, these all things are decided. So yeah, we will not talk about how these things are mapped to a task. We will consider this is mapped. Now that this is mapped, how should we schedule them? But if you learn about scheduling separately, read about scheduling separately, you need to know how do you decide these design parameters, but we will not go into that in this course. That will be too deep into scheduling. So yeah, but you can read that from the book that I referred. Anyways, so basically preemptive priority based scheduler, I told you what does it do. So I'll straight come to this slide where basically there are certain goals, optimality goals for scheduling different tasks. So all task executions, these are the constraints that the scheduler must follow. So must hold basically. So the first thing is the task executions must meet their deadlines, right? So as I told you earlier that if it's a hard deadline task, or the scheduler's objective is always to finish them before deadline, be it a hard deadline or soft deadline task. If it cannot do finish before certain certain tasks before their deadlines, then if you want to allow that particular schedule, that is up to you. And if that task is among those which will be allowed to have a soft deadline, then you will allow that particular schedule. We will come to that. Maybe it might sound a bit gibberish, maybe sound a bit far-fetched from here. As we see, as we go on, we will understand. Anyway, so feasible schedule is basically any schedule which does not does the above. Obviously, a schedule we consider a valid schedule or a feasible schedule where the deadline is met. When we say deadline is met, we mean the execution is done before the deadline, before or at the deadline, by the deadline, sorry. So, optimal with respect to feasibility, a scheduler that yields a feasible schedule for any task set, if such a schedule really exists, yes. So, if the task schedule exists or not, that depends on, is my screen visible? Is my screen visible? I think it was not visible. Is my screen visible now?
Yes, yes.
Okay, fine. So, yes. So, basically here the scheduling goal will be to meet the deadline. I have to finish before the deadline. So, yes. So, while doing so, the objective that I usually follow, that is basically I have to reduce the maximum lateness. What do I mean by maximum lateness? Maximum lateness is defined as the finish time of a task minus its deadline. So, if it is being finished after the deadline, that amount of that margin, by which margin it is allowed to be executed beyond the deadline, that should be reduced for each task. So, maximum of them is considered the maximum lateness among all the tasks in the whole task set. So, basically that should be reduced, that is one goal for scheduling them, and that is similar to this objective if you see, this constraint if you see. And another thing is schedule Makespan. This is a fancy term that is used just to say the same. What does it mean? Basically maximum of the execution finish time of each task, among among all the tasks that I have in the task set, maximum among them, and the release time, minimum release time, their difference, that should be another criteria that is considered as a schedule Makespan. So, that is also another criteria, so that we try to maintain. So, basically release time should be, minimum release time should be before the maximum finish time, obviously. I hope you understand that. So, we will see now how do we do it, how do we make a scheduling policy for that. So, yes. So, consider there is a set of tasks. Okay. So, in this set of tasks, there are n tasks if you see. So, they have a periodicity of pi, and they are the deadline is considered as the periodicity is always considered as deadline. As I was saying, these are considered as implicit deadlines of a task. When the task is periodic, the periodicities are considered as they are implicit deadlines. So, consider this is the task, here is the tasks that are getting executed. Okay. So, if you notice tau I, this particular task is getting executed given the highest priority. Okay. So first we see that this is of fixed priority. So let's see if it yeah, so gives the higher priority to task with lower periods. So here we are considering a scheduling policy called RM or rate monotonic. Okay, this is proposed by Liu and Leland. Okay, so this is very straightforward, as you can see that rate whoever has the highest rate of execution or the lowest periodicity, that will be the most prioritized task, because that comes most frequently. So here if it is a non-preemptive schedule, then basically this tau 1, since it has the highest periodicity, is considered to have a highest periodicity, so it will be executed before any other task. After that tau 2 will be executed. Why I am writing with tau 1 comma 1? 1 comma 1 means first task, first instance. Okay, first task, second instance, first task, third instance, or the third job of the task, like that. So anyways, if you see, if it's non-preemptive, then it will keep on executing and it will not leave room for this particular task, and you cannot execute it like that because you don't know to preempt them. Now if you allow preemption, so basically they can, the other task can be executed in between, right? This is getting executed, this is getting executed, this is getting executed, this is getting executed. So like that, it is preempted by some other task when it's needed. So basically, why it is preempted, by the way? Because for getting preempted, again, now we are not preempting whenever there is some other task in the queue. We are basically preempting only when there is need to do it, and the other task might miss its deadline if I don't preempt it, if I don't preempt some other task and execute that particular task. Okay, so that is when I am preempting that particular task. So now if I see among all the preemptive fixed priority schedulers, RM is optimal with respect to feasibility under the assumed task model with negligible context switch time. This is an important term to remember. This might be used afterwards. So what is context switch time? It is as the name says. So basically context switch time is nothing but the time that it takes while you are switching between tasks. How long does it take to switch between tasks? That time is called context switch time. Now that context switch time is considered to be negligible in case of RM. So considering that, otherwise you have to consider the execution or the response time of the task. While you are computing the response time of the task, you have to consider the context switch time as well. So anyways, in this case, if we are considering preemptive fixed priority schedule and the priority is designed based on the rate of the particular task, higher the rate, higher the priority. That means less the periodicity, higher the priority. Up to this, everything is clear? Any questions you have?
Sir, my request is, can we solve one problem, because then only the concept will be clear. Theoretically, we are clearing, but we are not able to,
Theoretically,
what
you
is
understand these
assimilate.
concepts. That is what you are trying to say,
Yes,
right?
yes.
Okay. So I should not waste time talking about these things. I should try to solve something,
Yes, sir.
right?
Little bit, so that that we
Understood.
will
Understood.
able to
Understood.
solve
I
the
had some
assignment
problems
also.
in
No?
mind. Okay. So we'll do that. So yes, I'll just quickly wrap it up and go to a problem. So yes, so this is happening here. This is basically saying that if you are executing by breaking it down, the overall execution time should be less than P1. So let's see. Up to what have we learned? RM scheduling, this is done. Yeah, let me finish this part. Basically, how this comes, you can refer to the book, and I will not go into the description how we are getting this particular formula. I think that is not explained in the lecture as well, is it? If it's explained in the lecture, then it's fine. Otherwise, you can refer to the book. There is a good explanation of this in the book. So yeah, so this is the, upper limit of execution that you have to follow, and this helps you understand if a particular set of tasks, where in the set of tasks if there are n tasks, what should be their utilization upper bound. Makes sense what I am trying to say? So, if the utilization is upper bounded by a certain value and that much resource is available for me, then I can schedule those tasks in a processor. If it is obviously less than 100%, then I can schedule them in the processor. So, that is how it is decided. So, here we are getting the ratio, what fraction of time it takes to execute from its periodicity of a task. So, let us see an example. In this case, there are 3 tasks, and Ci denotes their execution times, Ti denotes their periodicities. Now, it is very easy to compute if how much their utilization is. So, this is the utilization of these 3 tasks. Now, if I know there are 3 tasks, so for 3 tasks what is the upper bound of utilization, that also I know. So, since 0.75 is less than 0.78, this utilization is upper bounded by this. So, basically we can say the task is RM schedulable. These 3 tasks are RM schedulable in a processor, in a Uni-Processor. So, what will be the schedule? If you see, which one should have higher priority in this case? What should be the priority order in this case? Priority order should be as it is given in the table, tau 1, tau 2 and tau 3, right. So, basically what we will get is a schedule like this. So,
Sir, 0.78, sir, from where we get 0.78?
that is what I'll say it again. So, this is the upper bound of utilization that is allowed by RM scheduling. Okay. So, what do I mean? This is the upper bound. So, if there are set of n tasks, that set of n tasks for them, if I compute utilization, and what do I mean by utilization? Utilization meaning what fraction of time they take to be executed from their periods or the periodicities. So, basically they are ratios of execution times and periodicities. If we add them up for all n tasks, we get the utilization. If this utilization is less than equals to n into 2 to the power 1 by n minus 1, then they are RM schedulable. That is what I was talking about. I don't know, I don't remember if that is there in the lecture, how this limit is coming, but I think you can get it in the book that is referred here. Okay. This is where the 0.78 is coming from. Do you understand now?
Yes, sir, yes.
So it is RM schedulable, as you can see here. Now, if I come here, if I try to find out the schedule, then what should be the schedule in this case? Since I know what are their priorities, they are prioritized based on their less periodicity, higher priority. So, we considered a critical time analysis. What is critical time analysis? Basically, we consider at t equals to 0, all tasks have arrived. Tell me, when will all tasks again arrive? I mean together at their LCM, right? So, if each task is following a certain periodicity 6, 8 and 12, they will again arrive after 24 units of time, right. So, basically the tau 1 task arrives here and it is getting executed right away, right. So, its release time and start time both are 0. Is that clear?
Yes, sir.
But if you see task 2, that has a release time of at 0, but it is having a start time at when after this task is executed, because this has a higher priority in this case. So in this case, how long does it take to execute this task? 2 unit of time. So after 2 unit of time, it will start its execution. Since it's already in the ready queue, it is already released. So it starting from 2. So now tell me, what is the deadline here? So deadline, I told that for when I am scheduling periodic tasks, basically periodicities are considered as implicit deadlines unless we are giving some deadline explicitly. So usually we will consider this 6 unit of time as its deadline. So if you see, after every 6 unit of time, one tau 1 task instance is arriving, right? They are being released. So as they arrive, they are getting executed every time following this particular scheduling policy. So we will preempt if needed, we will preempt other tasks if needed, but we will definitely execute a higher priority task in this scheduling policy. Okay. So in this case, when it is done execution, and the execution is obviously done before its deadline, so it's a feasible schedule for tau 1. Now this should be valid for all the tasks. Let's see how it works. Since we know that it is upper bounded by this particular value, so we know that there should be a feasible schedule, but when I don't follow this upper bound, there may or may not be a feasible schedule. When I am not abiding by this upper bound, that does not mean I will not have a RM schedule. This is just a test that helps me understand when the RL schedule will definitely be there. Okay. So if it's not abiding by, if the utilization is not it is not abiding by this particular upper bound, then generally there is no feasible RM schedule. But we will see some examples, we will understand that by some examples, don't worry. So yeah, here if you see, the second task is being executed here, and all of the tasks have the same execution time too. This is to keep things simple. For a simple example, we will go to some complex example afterwards. So here if you see, after that tau 2 is getting executed, first instance of tau 2 and first instance of tau 3 is being executed here. Now they have different periodicities, hence different deadlines. Now if you notice, this particular instance, each of the task is being executed before their deadlines. In the second instance, this first gets executed. Why? If you notice, this has not arrived yet. So these three are executed for the first time. After that, it sees that this T1, second instance of tau 1, has already arrived. Now that it arrived at 6 unit of time, it will execute that. Now at 6 plus 2, 8 unit of time, it will find out that the second instance of tau 2 has arrived. Now it will definitely execute that. Now tau 3 has not arrived yet. So this part, if you see, there are no tasks. So the processor is sitting idle during this time from 10 to 12. Now at 12, since there are two tasks coming at 12, tau 1, third instance of tau 1, second instance of tau 3, right? Now which one should get executed? Obviously tau 1, because I know I am considering it as a higher priority task. So, and I am following an RM schedule, rate monotonic, that is basically fixed priority preemptive schedule. So here tau 1, third instance of tau 1 will get executed. After that, second instance of tau 3 will get executed. Why? You might think why the tau 2 is not being executed, because its new instance has not arrived yet. So once its new instance arrives, we will execute that, and by that time another instance of tau 1 arrives at t equals to 18, I guess. So then it's executed, and the hyperperiod is considered as 24. Why? It is the LCM of all these three periodicities of tasks. And why do we not proceed after this? Because after this, again this same scenario will be revisited. Is the example clear?
Yes, sir.
So this is the schedule that we are getting, and this is how we write schedules. So the subscript is meaning the task ID, you can say, and the superscript is meaning the instance number of the task. So this is an RM schedule.
Sir, how to write this schedule, sir? Please show it again, sir.
Here, can you see? Tau 1 first instance, tau 2 first instance, tau 3 first instance, tau 1 and tau 2 second instance of both, tau 1 third instance, tau 3 second instance, sorry, tau 3 second instance, then tau 2 third instance, tau 2 third instance, then tau 1 fourth instance. Understandable?
Yes, sir.
Fine. So this is called a ladder diagram. Basically, so this is how we. There are ways to draw schedules. This is one way to do it. It's like NAT charts that we draw. Anyways, so there is here is another example. Let's consider this and let's try to find out if we can schedule them following RM schedule. So as you can see, if we find out the utilization value for these two particular tasks, if you see it is greater than the particular upper bound. Now if you notice, earlier there were 3 tasks, right? Now there are 2 tasks. Can you see the utilization bound has increased for 2 tasks? So what happens is, uh, more the number of tasks, more it will be, the upper bound will be reduced. Okay, so if you see for 3 tasks it was limited by this. So this is a constraint that asymptotically eventually approaches to log 2. How does it approach to log 2? If you use a limit n tends to infinity. If you remember the limit formula, if we consider 1 by n as m, I don't have a pen so I cannot show you. If you consider limit n tends to infinity, and if you consider 1 by n as m, another variable, you replace it with another variable m, so you will basically get limit m tends to 0, 2 to the power m minus 1 divided by m, right? Is that understood what I am trying to say?
Yes.
So if you see, if you remember the limit formulas, this gives you log 2, which whatever is here, it will give you log 2. So what I am trying to say is, as we keep on increasing the number of tasks, it will saturate to a certain value. That value is log 2. So upper bound is asymptotically approaching log 2. Is that understood?
Yes.
So more I increase the number of tasks, more I constrain the upper bound. So yes, so this is someone joined. Yes, so if we decrease the number of tasks, in this case the constraint is a bit loose. So even after that, this is not abiding by the going by the constraint. So what will be in this case? So it might not be RM schedulable. As I said, this is not abiding by this upper limit. That does not mean there cannot be any RM schedules. This just means this fails the test. RM schedule, I mean feasibility of RM schedule test, it is failing. That does not mean there cannot be any feasible schedules. There can be feasible schedules, but mostly there will be none. So you have to still check if there is a possibility. So let's check in this case. So which has the higher priority in this case? Again, tau 1 has the higher priority because its periodicity is 5 units, and tau 2 has a periodicity of 7 time units, and obviously both are their implicit deadlines as well, and execution time also is varying, not like earlier where there were same execution times. So this is a generic setup, more generic setup than what we saw in the last question. So here if we see, if we try to schedule them, both of them are arriving at the critical moment, that is at time unit 0. At 0 time unit, since tau 1 has a higher priority, it will be scheduled. After that, so yeah, first thing, when you are drawing this, up to what should you draw? What did you understand from the last example? We should draw up to the hyper period. What is hyper period?
LCM of both periods.
Yes, LCM of both periods. So here, whatever lessons we are learning, everything we are learning up to the hyper period, because after that this will be repeated. Okay, same thing will be repeated. So anyways, so again, whenever we are asked to draw a schedule, we'll be drawing it like this, and then we'll be deriving the schedule, and then we'll be writing the feasible or the valid schedule. So here in this case, it will get executed starting from 0, and it takes 2 units of time to get executed. So at 2 units of time, it will be done execution, and then the next first instance of the task 2 will start, and it will be done before, what is its execution time? 4. So it will be done before 6 time units, right? But where is it ending? So 0 to 2 tau 1 is done. After that, sorry, 0 0 1 2, yes, 2, from 2 3 4 5, this is 5, I was wrong. So basically this is a wrong example. This should be 3. Consider this 3. This is wrong. If I have to go by this, it should be 3. This is wrong. Anyways, so for now consider that this is 3, and this is what you are getting here. This is how it is being executed. No, this is 4 only. So it is getting an overflow. No, sorry, don't get distracted. So this is 4. This takes 4 time units to get executed. Now since another instance of tau 1 is coming, it is being replaced by tau 1. So once tau 1 is done execution, another 1 unit of time it is left to be executed. So it is executed then. I thought I drew it wrong. So yes, no, it is designed correctly. So what is happening here? If you notice, tau 2 has a deadline of 7 time units, but by the time second instance of tau 1 is done execution, that is at 7 time units. So my deadline is missed. So this is not a valid RM schedule. Is that understood?
Yes, sir.
Now let's try to do it using EDF. Now what is EDF? So here there are descriptions how these things are done. I'll go back and through. I mean, I'll go back to the lecture, and then I'll again go back to the tutorial as I pass through those slides. So yeah, that will help, I guess. So hang on, again joined. Okay. So in this case, if you notice, uh, RM scheduling, why we are not always using that? So what is problem with RM schedule? The problem with RM schedule is, if you notice, if the schedules that we made, if we go back to the tutorial, the schedules that we made for an RM schedule had a lots of idle time, if you notice. So the processor is not fully utilized actually. Okay, it may promise, it may reduce the lateness. It is optimal in terms of reducing the maximum lateness. So in that case, RM schedule is good, but if we want to utilize our resources fully, RM schedule is not a good choice. So if there are less amount of tasks, RM is a good choice. Otherwise, if there are many tasks in your in the processor to be executed, then you should not choose RL, because that will resources will not be distributed properly. In that case, there will be many there will be huge amount of idle resources in that case. So here, EDF schedule, how does it work? This is basically a dynamic priority scheduling. Now there are different names. It is first told as, I guess, in the lecture, earliest due date. Okay, so this was proposed by, I guess, Jackson's algorithm. I think so. Now EDF is Horn's algorithm, earliest deadline first. So all these things are there in the lecture, so I'm not going through them. So if you notice, there is another example here. Yeah. So this is basically a dynamic priority scheduling algorithm, which will try to, I mean, using dynamic priority, it will try to optimally utilize the processor. Along with that, it will also ensure the feasibility of, obviously, the same way RM does. So it minimizes the maximum lateness as RM does also. So fewer preemptions. This is another gain that we have. I mean, there is some other thing that we gain from the from using EDF schedule. So EDF schedules lets us switch less contexts. So for RM schedule, there are more preemptions, so there are more context switching. So in this case, there are less amount of context switching. So it is better. So utilization is increased. We'll come to this later. We'll see this example first. So in this example, how EDF schedule works, we'll see the absolute deadlines. We, instead of considering the relative deadlines, we'll see the absolute deadlines of each task, and we'll assign their priority based on their absolute deadlines. What do I mean when I say I will look at the task from their absolute deadline perspective? Can you guess? You must have gone to the lecture. What do you think? What is different in EDF when I say that I have to look into the absolute deadline instead of the relative deadline? So basically what I mean to say is, starting from 0, let's not start from 0, let's proceed from 5. Starting from 5, what is the deadline for task 1 here? 10, right? So 10 is its absolute deadline, whereas 5 is the relative deadline that we are considering because its periodicity is 5. In EDF, we first execute. Obviously, here also the priority is same, but the priority is depending on the earliest deadline first, and here the deadline means the absolute deadline. So due date or deadline, whatever you call it. So basically this task is being executed where both of them are coming. At 0, tau 1 has a nearer deadline, that is 5, than 7 for the task 2. So task 1 will get executed. First instance of task 1 will get executed. Now task 2 starts execution. By the time it reaches 5 units of time, second instance of task 1 arrives. Now what is its absolute deadline of the second instance of task 1? What is its absolute deadline? I mean, it is understandable, right, what I am trying to say? Hello? Sir, am I audible?
Sir, audible, but what you want to say is not clear, sir.
Oh, okay. So when I said about absolute deadlines, that was understandable what I meant.
Yes, yes.
So in this case, if you notice, it is arriving at 5 units of time, and its deadline is 10. Why? Release time, when it's released, from then within 5 more units of time it has to be executed. That is how deadline works, right? We saw in that figure, right? Yes. Here in this figure we saw from release time before deadline I have to execute it. Is it understood?
Yes.
So at 5 units of time, this particular second instance of this particular task tau 1 is arriving. It has an absolute deadline of 10. But what is the absolute deadline of first instance of tau 2? 7, right? So it will
Yes,
not be
yes.
preempted. It will be, it will finish its execution, then only this will start. This is how it is differing from RM. This up to this, it is understandable.
Yes.
Now let's formulate the rest of the schedule. Now second instance of task 1 will be executed up to 5, 6, 7, 8. 8 units of time. By that time, the second instance of task tau 2 will already arrive. Now that will be executed. Now let's see, when it is arriving, there is no contention. Contention meaning there are no two candidates who are claiming the same resource. In this case, resource meaning the processor, right? Since we are talking about Uni-Processor, since they both cannot use the same processor, here the contention means both of them are trying to use the same processor, and there is no contention after uh, 8 units of time. So obviously task 2 will be executed, but at time 10 there is a contention. Contention means there is another candidate. There is another candidate that is ready to be executed, but which one should I execute? Again, same dilemma. So here, should I preempt? I would have preempted if it were RM schedule, right? So here what will I do? In this case, it has an absolute deadline of 14 and it has an absolute deadline of 15. So again, task 2 will be done with execution, then only the third instance, I guess, third instance of task 1 will start its execution. Same thing, after it is done, then what will happen? One, two, yeah, this is done. So again, at time 15, at 14, this task will arrive. Second task will arrive. Third instance of the task 2 will arrive. So by that time it arrives, there are no other tasks in the queue. So since the third instance of first task is executed, so it will start its execution from 14. At 15, there is some other task that is ready to be executed, that is the fourth instance of task 1. Do you see? So now let's see what are their absolute deadlines. So now the absolute deadline of third instance of task 2 is 21, but the absolute deadline of the fourth instance of task 1 is 20. So now this will be preempted. So the third instance of task 2 will be preempted by the fourth instance of task 1. Is this understood? Why is this happening? Hello? Hello? Am I audible? Sir, am I audible? Hello? Hello? Is this part understood? So here we see that task 1 is executed before task 2. Why? Because task 1 has a deadline that is nearer than the deadline of the third instance of task 2. Fourth instance of task 1 has a nearer deadline than the deadline for third instance of task 2. So likewise, after that, at t equals to 20, the fifth instance, 1, 2, 3, 4, 5, fifth instance of task 1 will be arriving. I am audible, right? Hello?
Hello.
Hello? I am audible? audible,
हाँ
right?
sir, what happened? Sir?
I am audible, right?
Yes, audible, audible.
This part is understood?
Sir, actually, I have gone for a break, frankly speaking, because it is 1.5 hours.
No,
So,
it's okay. Let me know if you feel like it's, I mean,
no, it is okay, sir. I understood,
take
sir.
a pause and then we can restart. We can take a
No,
pause,
it
5 minutes.
is
We'll
okay.
complete this.
Understood, sir.
So from next, from going next lectures, if you need a break, you can tell me. It's okay. So yeah. So what I was telling is, this part is understood. Now we are talking about. I think you did not hear this part here, where something else is happening. So at t equals to 14, third instance of tau 2 comes. Now, if you see, by that 14 time unit, execution of third instance of task tau 1 is done. Now there are no other tasks ready in the queue to be executed. Now third instance of task tau 2 is arriving here and it is starting to get executed. But at t equals to 15, fourth instance of task tau 1 arrives. And what is its absolute deadline? Its deadline is 20. But in that case, the third instance of task tau 2 has an absolute deadline at 21, right? So this has a nearer deadline and obviously this will be preempting the third instance of the task 2. Is this part understood?
Yes, sir. Yes.
So again, after that, after this is done execution, this will be finishing its rest of its execution at t equals to 20. Tau 1 fifth instance will come and it will be executed and it will be executed before the fourth instance of tau 2. Why? Because it has a earlier deadline, 25. So if you notice, once a task is getting higher priority, it will get higher priority up to some time. After that, it will again priority again will switch to some other task. So something like this happens in EDF schedule, and if you see in this whole schedule, no deadline is missed. There is no time overflow. So this is an EDF schedulable task, and how do you understand that? It is EDF schedulable because the utilization limit is here. Upper bound of utilization is 1. If utilization is less than 1, then it will definitely be EDF schedulable, and it utilizes the processor the most. If you see, there are very less idle time. So if this is understood, then we'll move on to the next. So there are other scheduling policies: LDF, latest deadline first, and EDF star. How are they different? LDF is just another policy that is, I mean, the scheduling policy handles the schedule, generates the schedule in a different way, but it is similar to EDF obviously, but it is a different, it is bit different because uh, it is optimal when there are task precedences. Basically, when we are giving an EDF schedule, we are not considering task dependencies or precedences. Here, if we have task precedences, LDF also works for such set of tasks. So here we will take an example, and EDF star. EDF star supports precedences. Along with that, it supports task arrivals as well. Okay, it is again another variant of EDF. So it supports new, if there are new tasks that are arriving. RM, EDF, all these are for fixed set of tasks. Okay, we know their priorities beforehand. Obviously for EDF we are changing the priority based on the situation, but yeah, those are for fixed set of tasks. But in this case, they consider the precedence relation between these tasks, and along with that they consider the arrival of new tasks and everything. So yeah, let's see another example. Check if the following task set is RM schedulable. If not, is EDF schedulable. Can you okay, yeah, it's again straightforward. So you will find that it is 0.78 which is sorry, 0.85 which is greater than 0.78. So you are not sure that if it's RM schedulable or not. If we check, we find one RM schedule actually. This is something exceptional. So do you see in this case, can you try to draw the schedule for this task set and match it with the solution here? So here the execution times are 20, 30 and 90, and the periodicities are 100, 150 and 200. So basically again you know the hyperperiod 600, so you draw till 600, and T1, T2, T3, this is the order of execution, this should be the order of execution if both of all three are there in the ready queue. uh, so I'll suggest, sir, you also try to find the schedule. That will help you understand what is happening here, and I'll keep on telling, and if you are stuck then I'll try to guide you, and later you can match the schedule that you are getting. So basically T1, when the first instance of T1 is coming, uh, that is getting executed, after that T2, after that T3, uh, but by that time T1 again arrives, so it will be preempted by T1 second instance. T1 second instance gets executed for 20 time units. After that T3 again starts execution, but by then T2 second instance arrives, so it will be preempted, and again the rest will be executed afterwards, because the another instance of T1 is arriving after that. So as it arrives, like this you can draw the schedule. Is this understandable, that how to generate schedules for RM schedules or EDF schedules? Is that understood? Hello? 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 So this is a schedule, RM schedule that we get for this task set. So I think by now you understand how to get RM schedules for a set of tasks and how to get EDF schedules for a set of tasks. I think that is clear.
Yes, sir. Yes.
So we'll come to LDF, one example of LDF scheduling. LDF scheduling is basically latest deadline first. So we'll start scheduling from the latest, the task that has the latest deadline. We'll start to fill the schedule from the end, what should be executed at last. So in this case we have to consider the precedence graph. This precedence graph, edges of the precedence graph are directed edges. Directed edges are basically meaning that the source task, the edge is directing to a certain task, right? So that particular task is dependent on this particular task from where the edge is coming from, the source of the edge. So this is how the precedence graph should be interpreted. In this case, if you see, J8 has the latest deadline, that is 20. I will place J8 at the last because there are no precedences. So J8 is
Sir, how
basically the,
to, sir, excuse me, sir, how to draw this graph? Can you briefly,
no,
sir?
no, no, you don't have to draw this. This will be given.
Okay, okay.
This is, understand this please. So this is basically tells the relation between these two tasks. So source of this edge is basically a task that is basically a task that must be executed before this task, where the edge is uh, destination of the edge. So the task at the destination of the edge, directed edge, is dependent on the task that is at the source of the directed edge. That is how this precedence graph should be interpreted. I will place the task with the highest deadline at the last of the schedule when I am sure that this task is not a dependent, I mean this another task is not depending on this task. If there is some other task that is depending on this task, that task should be executed at last instead of this one. Is that understood?
Yes.
We will see eventually that example. So, yes, so J8 will be placed at last, after that J7. Now, for J7 also there is no such task that is dependent on J7. So, I do not have to worry about if there is some other task that is dependent on me and that should be executed after me. So, I can be executed at last. So, J7 gets executed before J8. I am making the schedule likewise. So, after that, what has the third lowest deadline? J6. Now, J6 has a deadline of 18, and J6, where does J6 lie? J6, there is only one task that is dependent on J6, and that is J7, and that is already executed. If we start from the last, that is already placed. So, I can I can easily place J6 in the third place from the last. Once that is done, now there are what task is left? After J6 there comes J4, right? J4 is the fourth highest deadline. Now J4 has any dependent task? J6 depends on J4. J6 is already placed, right? So, J4 can be executed anywhere before J6. Okay. So, J4 will be executed before this. Now, after J4, which one is there? 15, then comes 12, J5. Now, J5, any other tasks that are depending on J5? So, J6 depends on J5, but J6 is already placed from the last. So, J5 can be executed any time. So, J5 is executed here, but that is coming before J4. What is that? So, after that J5 we are getting 8, J2. Now, J2 what are the tasks that are dependent on J2? There are J5, J4 and J3, right? Sorry, we did not place J3. J3 has 11. So, 11 J3. J3 has a dependency on J2, right? But J3 and which tasks are dependent on J3? J4 and J6 and J8. 4, 6 and 8. These three tasks are dependent on J3, but all of them are executed already. I mean, we have placed them from the last. So, we can easily execute J3 before them. So, we place J3 before J5. So, now what are we left with? J2 and J1. Among them, J2 has the highest periodicity, highest deadline, not periodicity, deadline in this case. So, deadline is 8, and what are the tasks that are dependent on J2? J5, J6, J4 and J3. All of them are already placed from the last. So, J2 is coming before them only, and I do not have to worry about if that should be placed or not. So, J2 is placed, after that J1 is placed. Is this understood how the schedule is done? Hello? Is it understandable what I am trying to explain? Hello? Hello? Am I audible? Now that we understand how to schedule, we'll do one more problem on EDF start scheduling. Sorry for the delay. Yeah, so basically WCIT analysis. So how does WCIT analysis work? So WCIT analysis is basically finding out what is the worst case response time. We know what is response time by the time the task is released, from the time the task is released up to the time when the task is finished. That is the response time of the of a task. So while I am processing, I am using processor, how long does the task take to respond, and what is the worst case value of it. And obviously, to find the worst case value, I have to repeatedly compute it until I reach a fixed point. So for worst case execution time, or the response time computation, not execution time, worst case response time computation, what we have to do is we have to find, this is the formula for computing this. Now this is computed like execution time of the particular task and plus the higher priority task, whatever higher priority tasks are there in the task set, from that task set, within the response time of the current task, what are the other, how many times the task can come. Excuse me, I'll come for 1 minute.
Hello, 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 hello. Hello.
Yes, sorry for the delay. Yes, so
Is now
yes,
now it is visible.
sorry, yeah, it is visible, right?
Yes, yes, yes.
Okay, so we were moving on to WCRT analysis. Now, EDF, so RM, EDF, LDF, and EDF star. Clear about all these schedulings, right? Hello,
Yes, yes.
fine, right? So, if questions are there from this, so which kinds of questions were you finding difficult in assignment? Physics assignment?
So there is message timing that we have not discussed. This is further in the lecture.
Fine.
When the message timing is there, then we have to block time and all that we have to calculate. Then this is the TDMA also. These are the, if you see the assignment,
Hmm.
the question is so heavy. It is difficult to understand also.
I mean, the question language is difficult to understand.
Yes, but it is so. I don't know. Some youngster may be finding it easy.
No, no, it's okay. That I'm trying to understand what is wrong in the question setup. We'll try to improve it. So yeah, but if you go through the lectures well, I mean, question should you should find the questions easy. So we'll move on to the bus part. So communication part, because this part you are saying it is okay to understand, because response time analysis everywhere is same. I'll try to generalize it first. So how to generalize response time analysis, worst case response time analysis? Basically, we are trying to find how long does it take. If you remember the figure that we showed you earlier, so that figure says whenever we are starting from, whenever the task is starting from that time, sorry, when the task is released, from that time when it is done, execution, finish time, between these two time periods, time units, we are finding the response time for that task. So it is taking that long to respond to the call. So now if we want to compute the worst case response time, we have to recompute it for multiple iterations unless we reach a fixed point. So in case of processors, it is very straightforward, but in case of communication buses, it's a little bit different. We'll come to that. We have don't okay, we'll continue as long as needed. So here in this case, if you notice, if we want to compute the response time, basically how long am I trying to am I taking to get executed, and after that within my current response time. Okay, within my current response time, here it should be R0. It should be R0. This is a generic formula. You follow this. So within my current response time, last response time that I have computed, current response time nth, at nth iteration, how many higher priority tasks can come, higher priority tasks can, how many times they can come, and how long they will take time to execute. Multiplying that means overall number of higher priority tasks that will be executing in front of me. Okay, so this whole number will give me the amount of time that is needed to respond against the call to execute that particular task. Is that understood?
Yes, sir.
So when we are getting in multiple iterations, when we are reaching a certain fixed point, we will say this will be, it will asymptotically I mean approach to a certain fixed point. So if we talk about, I'm not going into this calculation because there is a nice example that professor has shown in the lecture, I
Sir,
guess.
actually, sir, in this example, the last table is priority.
Last
So,
table is priority, yes.
yes. So, how to use this priority wala the thing in the
Here,
numerical, that please tell.
understand this. Here, this is message priority, I guess. Okay. So here depends on what policy you are using. Okay. If you are using RM policy, based on that, your computation time will be, your priorities will differ, right? In this case, the priority of T2 is highest. I think here it is following RM policy only, but here all possible parameters are given. This is not being used. uh, I mean, if there are no particular policy that are mentioned, then you have to take care of all particular properties of this task. And how I am using this priority? If you see this formula, here we are only considering the tasks which have higher priority. Okay. So, I am considering a priority, fixed priority scheduling policy, but it may be EDF, it may be RM, depending on the dynamically the priority may change or whatever it is, but at a certain time, if the priorities are given, then what should be its worst case response time, that is computed like this. So, if you see in this summation, there is only those tasks considered which have higher priority than task I. So, from this priority column in this table, you will understand if you are computing, consider this example, here you are computing for task 1, if there are other higher priority tasks. If you see for task 1, there is task 2 that is higher priority, right. So, we are computing the response time using that higher priority task. Is that understood?
Yes.
Now, if you see for task 2, there are no higher priority tasks than task 2. So, its execution time will be its response time. It will be always responded as early as possible. Is that clear?
Yes.
Any confusion? I find, I mean, it sounded like you had some confusion.
No, sir, I understood now.
So, understand this very well. This is to give you an easy example. Here dynamic priority is not considered, fixed priority is considered, and we are trying to find out what is happening. So, in case of dynamic priority, you have to find out if a set of tasks we are considering to schedule with dynamic priority, then we have to find out for all possible priority allocations, all feasible priority allocations. Feasible priority allocations meaning for those priority allocations for which deadlines will not be missed. I mean, there is a valid EDF schedule. What is the maximum response time? That maximum value will be considered as the worst case response time. Yeah, let's come to the bus scheduling now. Now, there are two kinds of bus level scheduling that are shown in this lecture. So, there are different kinds, but majorly two kinds you will find is time triggered and another one will be event triggered. So, CAN is basically event triggered, but in vehicles, in other in other CPSs, time triggered CAN is also used. Time triggered CAN is basically telling you when to exactly transmit a message, maybe after once every period or something like that. But event triggered, why CAN is event triggered? Why am I telling CAN is event triggered? We discussed about how CAN works, right? So, CAN is event triggered because whenever there is a message with higher priority in the bus, basically I am transmitting it to the bus, and that should be executed. I mean, sorry, that should be transmitted, not executed anymore. This is about bus. That should be transmitted in case there are multiple messages in contention and one has higher priority. That higher priority message will be transmitted. So, basically it is ideally an event triggered policy, but we can make it time triggered if we schedule the messages like that in the processor. Is that understood what I am trying to say?
Yes.
So, as you were saying, TDMA. So, TDMA works in a very simple way like round robin does, or can be a bit more defined than that. So, basically you know at a particular time slot you will send the data. There are fixed number of slots. You know, your basically TDMA specification will tell you what is the slot size, what is the length of the cycle, and how many slots are in a cycle. And depending on that, you will have to find out when a message will be transmitted. Did you understand this example that the professor explained? Hello, sir, did you understand this example that was explained in the lecture?
I have not gone through this lecture, sir. Abhi.
No, I request you to go through the lecture. That is fine. If you try to solve it without going through the lecture, it will be very difficult. I will try to explain you as much as possible, but I suggest you also go through the lecture, but I will explain. So basically what is happening here is this is a cycle, TDMA cycle. There are multiple slots. Slots have a nominal size. Those are spanning for a certain amount of time. Those are like periodicities. So S1, S2, they have same amount of time period assigned to them. So if we are transmitting something from 0 to maybe tau 1, so that is basically within the first slot, or if tau 1 to 2 tau 1, then second slot, like that. Is that understood?
Yes.
Now we will come to the message. So we are transmitting a message. Now where that message should be transmitted, let's find out from this example. So if you see, there are multiple tasks and there are corresponding messages. So only one task is transmitting message, that is M1. Okay. So we are talking about only one processor, I guess. Yes, one control unit. From one control unit, there are multiple tasks. One is task 1, T1, TS, I think sensing task, TC, I think control task, TTX, I think transmission task. So periodicities are given like this. These are their, I guess, offsets. Do you understand what do you mean by offsets?
Offset.
Yes.
Yes, sir. We understand offset.
Okay. So offset means basically when should we start the task. It might not start from the time it is released. Basically, if there is an offset given, it will count up to that offset from when it's released, and then it will start execution. Then it will go to ready queue. Is it understood?
Yes.
So it has an offset of 3. How is this offset chosen? When we do critical time analysis, we consider all of the tasks will be arriving at the same time. Without any offset, this would have executed before some other task. So this offset is basically working as a precedence. I don't need to. Ideally, instead of precedence, in this case, if we are doing something in an asynchronous way, we use offset. So when we say we are doing something in an asynchronous way, that means I will keep on transmitting periodically. Does not matter if I am done with the control computation or not, because that is what I should be keep on doing. I have to keep on transmitting. I should not be bothering about that. So if I keep on doing that, how should I ensure that I am transmitting the correct data? For that, I will add an offset to the task. After this amount of time, I am making sure from the worst case response time of the task TC that it takes 3 units of maximum worst case execution time, response time, sorry, not execution, response time. Its worst case response time is maybe 3. So after that I can place it, or I can see by when it is getting executed, then I can place it. And in this case, it is very easy to find out its worst case response time, because all the tasks are very pretty much visible here. So let's see how does it work. So this is how it is scheduled in the processor. EDF
In this, sir,
processor.
that offset time is 3. So because sensing time is maximum 3, so that is why we have took 3.
What do you think? Is that enough?
Sensing time is
Is
the
that
max.
enough?
Yes, sir. After sensing only we can control. So that is why 3 is taken as offset.
You can say that after 3 only TC starts execution basically. Do you understand this? After
Yes,
3
yes, yes.
only TC will start execution.
Yes, yes. That is why 3 is taken as offset.
Yes, yes. Okay. So after that, if we use it as an offset, then only I will transmit this proper data, that is that the TC is computing. So in another way, if you see it that way, that is fine. If you see another way, this is basically worst case response time for TS, isn't it?
Yes.
Or it will, the worst case execution time of TC will be less than 3. TC, WCRT for TC will be less than 3. Isn't it?
Yes, yes.
You compute and try to find out. So basically, yes, the idea is correct. So basically, since it cannot start execution before 3, so we are activating this particular transmission task at 3 with 4 periodicity. So T1 will be having highest priority, I guess. So it is a security task or some very high priority task that will keep on executing every now and then. So TS will come after that, then TC. Once TC is executed, it is having an offset of 3. So at 3 only TX is there, no other task is there, so it will get executed. And even though it has arrived at 0, here it is basically ready to be executed, and it will execute and transmit the message M1. So if you follow the timeline, it will be transmitted at 8th slot in the TDMA after transmission task is done transmitting that message. Is this understood?
Yes.
Now how can we know at which slot? Because we have told earlier, I think it is mentioned earlier in the question, that it has a slot size of 0.5 milliseconds or whatever the time unit is, and this is the cycle length. Is that understood?
Yes.
So this is how you find out when it should be transmitted. It is that easy. Is this understood?
Yes.
So yes. Now there can be some questions that will be asking you to do something in reverse. Maybe it will tell you need to send it in 8 time slot by 8 time slot because there is some constraint or something. Then what should be the offset of this task or something like that. Then you can back calculate, right?
Yes.
So that is what is required, I think, to solve the assignments. As much I remember. Anyways, that is one example. This is, I think, for another processor where you are receiving that task. Yes. So here are 3 more tasks. Here you are supposed to receive the task, and then you are supposed to actuate actuate the control message that you are getting to the task. T2 is another high priority security task or something like that. It keeps on running. So yeah. So once you are getting transmitted in this particular time slot, you are basically receiving it. Once T2, since T2 is having the highest priority, after that execution is done, you basically receive it, and after receiving it, you actuate it, and after actuation, again whatever you want to do, you are basically actuating to the plant. So again M1 is coming, again you are doing the same. This is how it is working. Okay, this is an example of a full flow. Yes, this actuation, sensing, computation of control input, and actuation. So for CAN, the worst case response time computation is a bit different, as I was saying, because it's kind of event triggered, but we can use it as a time triggered one. So here in this case, each message MI has total message size SI bits, right? The maximum transmission time over CAN. How do you compute that? SI into tau bit, where tau bit is the transmission time of 1 bit. So this, how do we decide this? This depends on totally what is my bandwidth. Depending on that, it is decided. So yeah, we will now see how to compute its worst case response time. Same idea again. Response time of a message MI is given by RMI equals to WMI plus CI. CI is my own transmission time, in this case not execution time, transmission time. WMI is queuing delay. Queuing delay means what? The longest time before the message MI gets access to the bus. That means there are other higher priority messages, other events that has the access to the particular communication bus. So once those events are done, then only I can get the access. Easy to understand. Now how do we compute WMI? That is the question. So blocking time. WMI is composed of blocking time. Due to lower priority, there are other messages, lower priority messages, that will be executed because they arrived before you. So there are two aspects. If there are multiple messages, they are arriving at the same time, which one has higher priority, that will be having the access to the bus. But if in the queue there are already previous instances of lower priority tasks, they will have to be executed. Is this understood? What I am trying to say, is this understood?
Sir, please repeat it again.
So, up till now, while we are computing something, we are adding something to the my execution time in case of processor in processor scheduling case. While I was computing my worst case response time, what was I doing? I was computing how long does it take for the higher priority tasks to get executed before me, that come before me, by the time I respond, right? But in this case, there are not only higher priority tasks, there are also tasks of lower priority, but they already arrived in, has the access to the bus in case of CAN, right?
Yes.
Unless they are transmitted fully, your bus is blocked for you to access. Even though you have wanted to transmit, it is not TDMA. You cannot transmit whenever you want. You will only be able to transmit when one message is finished. You remember the time frame, the CAN message frame from last class?
Yes.
Where was that picture? Yeah, yeah. So here, if you see, only based on this part, identifier, only based on this part, we are deciding which should get access. Remember from the last lecture, we saw that if someone has higher ID, a lower ID, that will get the access. Arbitration happens based on these fields. So once these fields are gone, still rest of the message should be passed, right? So how many such messages are yet to be passed? Based on that, you have to decide a blocking time, and that time, for that amount of time, your CAN bus will be blocked by the lower priority messages. So this is something extra in case of CAN compared to the processor level scheduling. Okay, so if we see this example here, basically blocking time is, this is the blocking time. So blocking time is 12 milliseconds. Why 12 milliseconds? For message 1, if you see, what are the lower priority tasks than message 1? Message 1 has a lower priority task, that is M3, and M3 has a transmission time for 12 milliseconds. So 12 milliseconds is the blocking time for M1. And for M2, M2 is the highest priority message. So for M2, what are the lower priority messages? M1 and M3. Among them, which one has the highest execution time? This is the formula. Among all the lower priority tasks, which one has the highest transmission time? So again, it will be 12. So blocking time for both will be 12, but the third message, there are no lower priority tasks, so it will not be blocked. But if there are higher priority tasks, then there will be busy period. This is something that is similar to the processor level scheduling. So what is busy period? Busy period TMI of a message MI is the time duration starting from the critical instant till all the released instances of the message MI are successfully transmitted. So this is basically a busy period until which I am done with transmission. If there are multiple instances of a message M1 until all of them are transmitted, that is it is still in its busy period. Is that understood? I'll explain this example. There is a confusion, I understand. So see, there are three messages again. In this case, which one will have the highest priority? So there are multiple instances, 0th instance, then first instance. So in critical instance, multiple messages will arrive. Now when I say multiple messages will arrive, M1, M2, M3, if all of they arrive, M3 will not be executed then because it has a lower priority. If they are arriving at the same time, first thing what will be executed is last instance of M3. Is that understood? I am seeing starting from a timestamp. Last instance -1, it is not written. So blocking time will be covered first. What is the blocking time for task M1? That is 12, right? Why? Previous instance of M3 might yet to be transmitted. I am computing the worst case possibilities. So I have to consider this. Is this understood?
Yes.
So considering the worst case, when I am about to transmit my message, at that time the lower priority messages are yet to be transmitted through the bus. So once they are done, once my blocking time is over, I am ready to be executed. Sorry, not executed, sorry, transmitted, right? So how long do I take to transmit? 8 units of time. I have the highest priority, I am M2, first 0th instance of M2, and I transmit myself, right? But by this time, first instance of M2 already has arrived. Okay? If that has already arrived, then that will have to be executed, I mean not executed, transmitted, and then M1 0th instance and M1 first instance will be transmitted. So overall busy period will be, by the time, since there are 2 instances of M2 now, for M2 busy period will be, by the time, sorry, for M1 we are computing for M1. For M1 when both of them are transmitted, sorry, for M1 busy period will be by the time both instances of M1 are transmitted. Is this understood? Which part did you not understand? If there is a confusion, I'll recall again. So this is the blocking time for both M1, sorry, M2 0th instance gets transmitted. M2 another instance comes that has the higher priority, so it will get transmitted. After that, M1 0th instance will get transmitted, and since by that time M1 first instance is already arrived, M1 first instance will also get transmitted. So this whole time is its busy period. If there were no first instance of M1, we wouldn't have computed up to this. We have to have computed up to this. This would have been 33.
Sir, where is M3? M3 in this?
M3, that is what M3 will come after, will be executed after this, because that has the lowest priority, right? 0th instance of M3 will be transmitted after this.
Okay, okay, okay.
We are only trying to prove the point that the busy period for M1 is 38 milliseconds. How? We are considering the last instance of M3 is yet to be transmitted. After that, 0th instance of M2 will be transmitted because that has the highest priority. By that time, if first instance of M2 comes, that will also have to be transmitted. So I will be blocked until the last instance of the lower priority messages are passed, and the same current instance of the higher priority messages are passed. Then only I can transmit myself. So this whole time is busy period. Is that understood?
Yes.
So basically you are adding with, how are you getting it? So if this is the busy period, you are adding the blocking time, you are blocked for some time, then you are waiting as long as your higher priority tasks are not transmitted, and that is how we compute that exactly. Do you see? So this means what? This will help me understand how many times my higher priority task is arriving. This is similar to the response time calculation. This is busy period computation that we have to do iteratively, then we have to convert it into response time. So first for busy period computation, we'll do it iteratively. For the last iteration, whatever my busy period was, within that busy period, how many instances of a higher priority task can come, or how many instances of my current myself can come. So that many times it will be arriving, and then it will be multiplied with its transmission time, and the overall time will be my busy period. Is this understood?
Yes.
Okay. Now convergence will be guaranteed as long as utilization, again similar concept like processors. Here utilization means using the bandwidth. Transmission time divided by the periodicity is less than 1. Summation of it is less than 1. As long as me and my higher priority tasks have a utilization that is less than 100%, I am sure that my busy period will be within a tolerable range, and I will be converging to a busy period. Busy period will not diverge, it will not keep on increasing. Understood?
Yes.
So let's see an example. This will help you understand the whole idea. So for the same setup, we will have busy period for M1 is basically 12. So let's compute what is the busy period for M1. So BM1 is 12. We computed that because its lower priority message is M3, and M3 lower priority message is only M3, and M3 has an execution time of 12. Now for the first iteration, when I'm sorry, this is the first iteration. First iteration is basically computed with its transmission time, my own transmission time. So M1 has a transmission time of 5. That is what it is. Its busy period is yes, busy period is. Now in the first iteration, its busy period is basically the blocking time plus within the 0th iteration busy period, how many instances of a higher priority task, a task that is of higher priority than me or myself, is arriving. So a task that is of higher priority than me, that is M2, right? M2 has a periodicity of 20, right? So within 5 unit of time, how many times it can come? Within 5 unit of time, how many times I can come, my instances can come. If you notice, this formula has not only HPMI, it also has union of MI. Remember this. So higher priority task than myself and me, how many instances of myself and my higher priority tasks are coming? Busy period includes all, like the example. Okay. So here we are computing for all of them 25. Second iteration, we are replacing this 5 with 25 and computing 33. Now if you see, for the third and fourth iteration, we are converging to a particular value, that is 38, and 38 is the busy period for M1. For M2, again the same thing is computed. It's very easy because M2 is highest priority, so nothing to worry about. For M3, again for M3 it will be computed the same way. You look into it. For M3, notice that blocking time is 0. Why? There are no lower priority tasks than it, right? So busy period, this busy period should be less than or equal to its periodicity. Okay. So if it's like that, then fine, then you are executing before next instance of your message is arriving. If not, then basically if your busy period is larger than your periodicity, basically multiple instances are arriving, and when you are done executing, that is your busy period, right? Is that is understood, right?
Yes.
So how many times you are arriving in busy period, that you can compute easily from your periodicity, getting a ceiling of your periodicity. Okay. Now that you know how many times you are arriving, So basically, response time analysis should compute response time of all these many instances, right? Is that understood?
Yes.
So basically you find out the longest response time among them. Longest response time is nothing but basically you know this many times it is coming. So you are basically trying to compute for the first one what is my busy period, what is my blocking time and everything you are computing. For q equals to 0 you are computing it, for equals to 1 you are computing it, because you are getting a 2 value. So you are computing it for 2 of them and you are considering the maximum among them. So if you notice here for M1, it is 33, I guess 33. For M1 second instance it is 8 milliseconds. Remember this figure, right? So in this figure if you notice that first instance of M1 is done execution as I told earlier within 33 seconds. So this is the busy period for it, right? For the first instance, for the 0th instance, its busy period is 38. For the first instance, its response time is 33. Understand these two differences. Response time means when I was ready to be transmitted and when I am done transmission. That is the response time, which is 33. And for the second one, it is here it is arriving, here it is transmission is done. So it is 8. Among 33 and 8, you are finding the largest one is 33. So this is your response time. Is this understood?
Yes.
So now formulate it. Let's formulate it. How do we formulate it? This is how we formulate it. This is the formula for longest response time computation. So basically up to this you know, this is basically busy period. We only added this and this. Now there is a new term Q into CMI. Q means what? How many times am I arriving within the busy period, right? Based on the change in the Q value, you will see this particular value will change, right? You compute the response time like this. You compute this one minus Q into PMI plus CMI. So basically you are from the overall busy period that you are getting, you are negating the at qth iteration the periodicity of your task, that particular task multiplied by how many times it is arriving within the busy period, and you are adding execution time of that particular task. This is the formula. If you notice here the same thing is happening actually. From 38 you are negating, basically if it is 2 you are starting from 0 and then you are going to 1. So you are negating one periodicity and you are adding one transmission time again. So and you are getting 33. So you compute it for an example. For this particular example only, if you compute it, you will understand how this formula is working. But this is the formula, and here again you have to do it for multiple times. Multiple times meaning for multiple Q values. For each Q values, you have to compute the busy period multiple times. So we have seen how to compute the busy periods. Maximum busy period will be computed like this. Now you know how many times it will be arriving within that busy period. Now that you know this, now you have to compute these values for each Q. Now for response time computation, you compute the response time, just put these values in this formula. Is this understood? This is a bit complex, I understand, but this, anything that you don't understand in the description, in the formula, any term that you don't comprehend, cannot comprehend. let's see this example. So M1, for M1 we are computing, let's try the same thing by using the formula that we did intuitively. So for M1 we know blocking period is 12. In this formula you see there is one tau. Do you remember what we used tau for? Tau was for at least 1 bit message. How long does it take for at least one bit message to be passed? That will be a very small number, but since we are taking a ceiling here, having a tau value, when both of these are equal, that will end up in giving you 2. Is that understood what I am trying to say? If there is even a little amount of margin in this tau value, your ceiling value will be increased by 1. Okay. So that is why, since we are computing everything in worst case, so we are using this tau value here. So let's see for this message 1. So for message 1, there are 2 instances possible. We have computed the busy period. We know q equals to 2. Now for q equals to 0, bm1 equals to 12. Okay. So what do we get? 12 plus 0 into 5. Why 0 into 5? Here in this formula, 0 into 5. 0 is the qth instance, 0th instance, and this is not yet coming because that is the 0th instance of this particular task. There are no higher priority tasks before it. So for 0th instance we are getting this. 0th instance will be computed like this. In the first instance, if we see, blocking time is 12, and along with that this is 0, so you are not writing it. Higher priority message is there. Which one is my higher priority message? M2, right? M2 has a periodicity of 20, right? So 12 is the blocking time, sorry, not blocking time, sorry, 12 is the W0 M1. Okay. Busy period for the 0th iteration, for the 0th instance of task M1. We are using that and we are dividing it by 20 and we are getting 20, right? We compute it again for 0. How do we compute it? Again we use whatever blocking time is there. Along with that we compute the 20. Last time what we computed, W1 is 20, right? 20 plus tau bit divided by 20, because 20 is my new updated busy period for the 0th instance, and now I am computing it for the second iteration. Here I am changing it and I am finding a new value, that is 28. For the third iteration I am computing M10 and I am getting again 28. So basically 28 is the busy period and this is the response time for the 0th instance of this particular message, but I am trying to compute what? Worst case response time. So basically what will I do? 28 minus q, 0 into pm1 minus 0 plus 5. So I will get 33. So what does this actually mean? After 28th time unit, here I am able to transmit through the bus. After 5 time units after that, I am done transmitting. So this is my response time for the 0th instance. Now there is one more instance coming. If you compute that for one more instance, you will get the value 8, like we got it earlier, 8. Now among 8 and 33 you will find out that 33 is larger, so we will decide the worst case response time is 33 for M1. See, here we are getting 8. Okay, there also you will get 33 only, I guess, but if you negate it with 1 into periodicity, you will get 3 plus 5, 8, and among 8 and 33 we get 33 as the response time. Is this understood?
Yes.
Now I suggest you to go through the lecture. It will clarify things even more. Okay. So this summary is also explained there in very well. So you go through the lecture after this. most of the questions that you will get, either that will ask you to compute the response time in Canvas, or it will ask you to find the offset, or it will ask you to find the slot length, or it will ask at which slot the message will be transferred in TDMA, or it will ask you to find the schedule following EDF, EDF star, LDF, or RM schedule. These are the only questions that we will see in these assignments. Are the things somewhat easier now?
Yes, sir. Again, we'll start and then we will respond.
Okay. So you go through the, I am suggesting, sir, you please go through the professor's lecture. Then I think you'll understand. If you don't understand something, you can mail me directly. I think I initiated a mail chain. There, if you have any doubts, you can mail me there. You will see the TS of this course has initiated a mail chain with my email address CCing there. You can reply there. If you have any doubts regarding anything, I will explain that in my session. Is that fine?
Yes.
Okay. So we'll end our session here today. So we'll meet again next week. Okay.
Thank you, sir.